Okay, we're going to talk about section 6.1 right now. Chapter 6 deals with random variables. It's the next step in regards to probability. Probability is basically 1/4 of the course, roughly 1/4 of the questions on the AP Stats exam deal with probability, which is really pretty much Chapter 5 and Chapter 6 to us. So Chapter 6 has some nice challenging problems, and it's going to take some work and studying, but I think you can figure it out by looking at a number of different examples and problems, and anyway. But what it deals with is random variables, and basically, random variables are basically the outcomes of a random phenomena that it's a numerical outcome of some chance process. So it is a numerical outcome of a chance process. It's basically something that produces a number. It's going to be, and when you define a random variable, you can just call it X or any letter you want. It's sort of traditional to use X and Y, but you can use any letter, and you typically use a capital letter. But X is equal to some number is the thing. It has to be a number. It can't be something that's not a number. So in regards to people, a random variable would be like X is equal to someone's weight. So you'd say X is equal to someone's weight in pounds, like 172.68 pounds or 142.271 pounds. So, or it could be X is equal to, let's say, the number of siblings someone has. They could have 0, 1, 2, 3, or 4. But it couldn't be X is equal to like their political party affiliation, because that's not a number. So, or it certainly could deal with anything like, let's say, with trees. So a random variable would be X is equal to the height of the tree in feet. Or let's say the number of fruit that a tree has. But anyway, but it couldn't be something like flipping a coin and the results are heads and tails. That's not a number. So in order to be a random variable, you'd have to define that as X is equal to, let's say, the number of heads you get when you flip a coin 3 times. So then it's a random variable because you've established it as a number. There's 2 kinds of random variables we're gonna deal with, and so we have a discrete random variable. A discrete random variable has a countable number of outcomes, and I think once you look at a decent number of problems, you're going to be able to clearly distinguish between a discrete random variable and a continuous random variable. But it has a countable number of outcomes, which a lot of times, but not always, are integers. It could be something like X is equal to the number of cars that a family owns. So it could be 0, 1, 2, 3, or 4. It could be X is equal to, like, let's say, the number of fruit in a tree, or X is equal to the number of AP classes that someone takes. But it has a countable number of outcomes. And there's the one way you can tell it is there's gaps between the values. Gaps between the values. And typically the way you define it is it's going to be X is equal to the number of something. The number of something, the number of siblings that someone has, or the number of math classes someone has taken, that sort of thing. A continuous random variable can take any variable in an interval, can take any value in an interval. So typically it will contain decimal values. So people's weight, they could weigh 126.287 pounds, or their height, they could be 67.562 inches tall. It could take any number in an interval, and there's no gaps like there is in a discrete random variable. And so typically we say X is equal to the amount of something. The amount of something. So, and I think once you look at a number of examples, you'll be able to tell the difference between discrete and continuous. But in continuous random variables, there's no gap between the values. It can take any number. It can take an infinite number of numbers, so to speak. But in a discrete, it has a countable number of outcomes. So one example would be, let's say, in regards to, let's say, shoe size. Now, in shoe size, you would have, it could take on values like, 8, 8.5, 8.5, 9, 9.5, 10, but you really wouldn't be able to have a value that's in between 8 and 8.5. Okay, and that'd be an example of a discrete random variable that could take values that aren't integers, has a countable number of outcomes. But a continuous random variable that would be similar to that would be like if x is equal to the length of someone's foot. Now, that could be, 10.278 inches. It could take any value in an interval. It's not confined to just 10, 10.5, and 11 like shoe size is. But we'll start with random variables. So we'll start with discrete random variables. So the first example here deals with the number of car accidents in a town is shown below. And so here's our discrete random variable. It can only take one of 5 values. It has to be 0, 1, 2, 3, or 4. So in this particular town, the number of car crashes each week is either going to be 0, 1, 2, 3, or 4. And 0 occurs 50% of the time. So this is a probability model that shows each outcome and its probability. 1 occurs 20% of the time, 2 occurs 16% of the time, 3 occurs 11% of the time. And so the question is, what does 4 have to be? And you need to realize in any probability model is that the probabilities have to add up to 1. Something has to happen for this to be a true probability model. And so these, in fact, add up to 0.97. So this has to be 0.03. So that would be the first thing. And so sometimes it can give you a probability distribution and ask, is this a probability distribution? And you have to make sure that these things add up to 1. And it could ask you what's the probability that x is equal to 4. It could ask you, for instance, what's the probability that, x is greater than 2. And so you would just say, well, greater than 2, that means it would be, to show your work, show the addition. Show the addition. So greater than 2 would be 14%. Right there, which is distinctly different, by the way, than greater than or equal to 2. Greater than or equal to 2 would include 2. And so you would say, well, that's 0.16 plus 0.11 plus 0.03. And so that is going to add up to 0.3. So that would be 30%. In a continuous random variable, by the way, is greater than and greater than or equal to are the same thing, believe it or not, and we'll get to that in a minute. But in discrete, it's important to realize that greater than is not the same as greater than or equal to. Same thing with less than and less than or equal to. But so let's look at this. This will be a new sort of problem for us. Given that there's more than one crash, what's the probability there would be more than 3 in a week? And so using the notation of the last chapter, all right, so given that our value of x is more than 1, so greater than 1, what's the probability there will be more than 3, that x is greater than 3? Now, as we discussed last chapter, this is a conditional probability. This is a given. Well, that's the probability of both of those things, A and B, so to speak, so that x is greater than 3 and x is greater than 1 over the probability that x is greater than 1. Well, what's really the better way of saying that x is greater than 3 and it's greater than 1? Well, for something to be greater than 3 and to be greater than 1, it has to be just greater than 3. So that is, in effect, the probability that x is greater than 3 over the probability that x is greater than 1. So x is greater than 3, that's 0.03. It doesn't include 3, so this would be 0.03. The probability that x is bigger than 1, well, that includes all of these, which is same as greater than or equal to 2, by the way. And so that is equal to 0.3, and so that's equal to 10%, or 0.1. And so that would be showing your work there. So these conditional probabilities in this chapter just end up being the probability of this over the probability of that is what ends up happening. Now, you will be asked to make a histogram of this situation. And so all you would do is this. So to make a histogram, you go like this, and you'd say, well, first of all, on the y-axis is just probability on the vertical axis. And then on the x-axis, we'll put our number of crashes. And so make sure and label. So this would be 0, 1, 2, 3, and 4. And so this is number of crashes in a week. Okay, so it could go up to 50%. So the biggest one is 50%. So 1, 2, 3, 4, 5, 0.5. And of course, you have to just write down two numbers to get credit for scaling. So I properly labeled and scaled it. And so 0 goes up to 0.5, and so that's that. And so 1 goes up to 0.2, and so it's there. And 2 goes up to 0.16. And of course, we just in general want to see what's happening. It doesn't have to be perfect, but it needs to be reasonably neat. And then 4, there's not a lot of 4s. And so there's our distribution. Describe what you see. Well, we would cuss. You would say, well, it is definitely strongly right skewed. That would be the shape. It would be strongly right skewed. Right skewed. So that would be the shape. You'd see it's centered around 1, I would say. We're fixing to find the mean that would describe that. So we would say it's centered near 1. You'd say that the range is just 4. That would, in essence, describe the spread, and we're fixing to find the standard deviation on this thing. And then there doesn't appear to be any outliers. All right, what is the mean? All right, now, so here is how we're going to define the mean, and there is a formula for this, and there's two formulas. There's a couple of formulas on your formula sheet that deal with this situation. And I'm gonna write them out. But so here is where we took off on our formula sheet in the last chapter. That was our general addition rule in chapter 5, and that's our conditional probability there. Here is these two that come into play. Here is the expected value or mean of a discrete random variable. And so we'll look at that. It is just going to be every value of x times the probability, and then that sigma means add them up. And then this var means the variance. It is the square of the standard deviation. And so we have a little formula for that we're going to use. And just remember, when you find the variance, to get to find the standard deviation, you take the square root. And that's going to be, the variance is going to be a really important concept in this chapter. And so first of all, to find the mean. So the little formula for finding the mean is mu is just the sum of the x times p. So we take every value of x and multiply it times its probability and then add them up. And I can just show that on this table. So I will just multiply these. And so I say that times that is 0. So I'd say that times that is 0.2. So that times that is 0.32. And then that times that, just multiplying all of these. So that times that is 0.33. And then that times that is 0.12. And then let's see, when you add these up, they add up to 0.97. And so when you sum these things, when you add these up, that's equal to 0.97. And that 0.97 is our mu. So our mean in this case is 0.97. And showing your work is just showing that. So it's important to show your work. And I'm going to show you how to find this with your calculator, but you have to be able to show your work in essence and that's 0.97, not 0.92. So we have that. Now, the standard deviation is a little more complicated to be able to find the variance in standard deviation, and there is a shortcut with your calculator, but let me show you how to do that. So the formula there that is on your formula sheet, so there it is. So the variance is going to be equal to the sum of, and if you take x minus the mean, square it, and then multiply it by its probability. So what we're going to do is we're going to take every value of x up here, all the 0, 1, 2, 3, or 4. We're going to subtract the mean of 0.97, square it, and multiply it by its probability. And so here we go. And so that's what I'm going to do. So here's every value of x. So I'll start with 0, and I will subtract the mean. So this would be 0 minus 0.97 squared, and multiply it times 0.5. All right, and so let's see what that is. And so this would be 0.97 squared, and then times 0.5. And so that is equal to 0.47045. Then do the same thing with 1. I will take 1 minus 0.97 squared and multiply it times 0.2. And so that would be 0.03 squared times 0.2. And so 0.03 x squared times 0.2, and so that is equal to 0.00018. Then I do the same with 2. 2 minus 0.97 squared times 0.16 multiplied by its probability. So we will do that operation, squared times 0.16, and we would get 0.1697 approximately, and then we have 3 minus 0.97 squared times 0.11, and so when we do that, 3.97 and squared times 0.11, and so that is equal to 0.4533 approximately. And lastly, sort of running out of room here, 4 minus 0.97 squared times its probability is 0.03, and so that would be 4 minus 0.97 and then squared times 0.03, and so that is equal to 0.2754. And so when we do that, when we add all of these numbers up, that is the variance. That is the variance. So our variance is when I sum all those numbers up, which I believe is 17, which I believe is 1.3691, and so I can take the square root of that, and that is equal to 1.7009, and that is the standard deviation, and that's certainly very tedious. Now, but let me say this: knowing how to do this by hand, yes, you need to know how to do it. You need to know how to set it up, and I'm going to show you how the shortcut with your calculator in that regard. But the real important thing is not really doing this. The important thing is to be able to describe these things in context, because frequently they'll just give you these values, but stating these things in context, just like we did earlier in the year, is a really important issue. So what does this number mean? What does the mean mean? And so what it is, this mean of 0.97, what that is, if we were to look at many, many weeks, many, many trials, on average, the number of crashes we expect to be 0.97. So that's what you need to say. If we looked at many, many weeks, we expect that the average number of crashes will be 0.97, and don't round that. It's very important that you don't round that. Don't say, well, it's going to be about 1. Leave it as 0.97. And you have to say it this way. If we were to look at many, many weeks, don't say, oh, if we were to look at 1 week, we would expect there to be 1. So that's not really the concept of what a mean is. The mean is, if we were to look at many, many weeks, we're expecting it to be that, and make sure and don't round it. And the standard deviation is the same thing it meant earlier in the year. It's the average amount that our points are varying from the mean, or from the middle. So it gives us an idea of just the average variability going on, and so we say the same sort of thing in a way. So you'd say if, so that's stating the mean in context, and then the standard deviation in context. Standard deviation, if we looked at many, many trials, as we would say, or many, many weeks in this case, because that's what is in the problem up here. If we looked at many, many weeks, we expect that the number of crashes will vary from the middle, or from the mean of 0.97 by 1.7009 on average. So it is the standard deviation is the average amount that our points are going to vary from the middle. So that is, and so this is really important. Being able to do this stuff by hand like this is not critical. And in general, what I encourage you to do is use your calculator to find these, which is what I'm fixing to show you, but to show your work by showing a couple of these. And so you can look at the formula that's on your formula sheet and show a couple of things plugged in, and then use your calculator to find it. So this is how you'd find the mean and standard deviation using your calculator, and you're probably not going to be too thrilled about doing this by hand when you see how quickly you can do it with your calculator. So if you have a discrete random variable, you've got this list of numbers and their probabilities, and you're asked to find the mean and the standard deviation, what we can do is put them in a list. Okay, so I'll go stat, hit the stat button, and then hit edit. And then I'll just put these numbers in a list. So I've got some, let me clear these out. So I hit clear and down arrow to clear these lists. So clear and down arrow. All right, and so I'll put the x values here. So 0, 1, 2, 3, and 4. And then in the list 2, I'll put the probabilities, 0.5 and 0.2 and 0.16 and 0.11 and 0.03. So I believe I've entered those right. And so now what I'm going to do is I'm going to do one variable stats with list 1 and with list 2. All right, and the same thing. This is the only time all year we're going to put something in the frequency list aside from 0 or 1. So I'm going to go to one variable stats, stat calculate, one variable stats. So in the list menu, I put list 1. So I do second 1. Now it'll probably say nothing there, so I want to put list 2 in the frequency list. So what that's doing is it's taking the values of list 1 and using them in the frequencies that we put, or the proportions that we put in list 2. This is the only time we'll do that. Make sure for the rest of the year, there's nothing here, either blank or 1. But anyway, and so we hit calculate, and hopefully I get it right. Yes, I did. And so there's the mean, all right, which is listed as x bar. We call it mu. And then there's the standard deviation. It's the only time all year we'll use that sigma as well. So it's about 1.17. If you were asked what the variance is, you would square the standard deviation. So that is how you use it with your calculator. If you're asked to do this on the exam, you could certainly use your calculator to do that, but show a couple of times where you have showed it plugged in to where you've shown that you know how to use the formula. That would be considered showing your work. And so that's discrete random variables that we're going to be doing a number of problems on to try to get good at. Now we have continuous random variables. Continuous random variables aren't a countable number of outcomes, and discrete random variables will all pretty much look like this. They'll have a countable number of outcomes where it's impossible to have a number of crashes here that is in between these numbers. But we'll have something like, let's say, an amount of time. And so in this case, we've got an amount of time, so that it varies between 0 and 7 hours. So it could take any number in there, and there's actually an infinite number of numbers between 0 and 7. It could take 1.265, or it could take 6.27812. Okay, so there's really an infinite number of numbers. So this is not a discrete situation. It is a continuous situation. So it says the amount of times that workers at a factory spend in training each month follows a uniform distribution. Uniform. Now what that means is it's going straight across. It's distinctly not normal. So there's really three sorts of problems in this section. We've got the discrete random variables, we've got the uniform, and then we're going to have the normal curve problems similar to what we had in chapter 2. So what we've got here, so we've got a uniform distribution that varies between 0 and 7. If you randomly select a worker, what is the probability he spends greater than 5 hours in training? So the way I do this, and there can be kind of different ways to do this, I just show the numbers, okay, 1, 2, 3, 4, 5, 6, 7. So there's 7. Uniform just means it's going straight across. It's making a rectangle. Is that everything's occurring equally. And then I like to just block it up in areas to find probabilities. So if you randomly select, so each one of these points in this rectangle represents a time, in this case, that they spend in training. And so if you randomly select a worker, what's the probability spends greater than 5? And so what is the area that's above 5? I tend to just say, well, I'm going to say the height of this rectangle is 1. So the area here that's greater than 5, that's an area of 2. So the probability that x is going to be greater than 5, all right, well, that area is 2 over the total area. Well, what's the total area here? The total area, is 7. It has a length of 7 and a height of 1 is 7. And so that's the answer, 2/7. Okay? So, and so to me, that's the way I handle it. Some people just think about a number line. If you randomly pick a number between, 0 and 7, what's the probability it's greater than 5? And you say, well, from 5 to 7 is 2, and from 0 to 7 is 7. So it'd be 2/7, and that works. Now, here's a bit of a paradox, which I alluded to earlier, is what is the difference between greater than 5 in this situation and greater than or equal to 5? Well, if you think about it, equal to 5 would just be this line segment. And what is the area of that line segment above 5? It has an area of 0. So it's sort of a paradox. If I add on the number 5 onto this, it's adding 0 to the area, so it's actually still 2/7. That's true for any continuous curve. Is greater than and greater than or equal to are the same thing in a continuous curve. And the same thing's true in a normal curve. All right, whereas that's not the case in a discrete. In a discrete, as we mentioned earlier, greater than 2 is distinctly different from greater than or equal to 2. Okay, so anyway, and then the second thing we're asked here is we're asked, what about greater than or equal to 5? So it says, what is the probability that, that's what we just said, never mind. Here, the next problem. So if you randomly select a worker, what is the probability they spend greater than 5 hours given they spend greater than 3? So the probability that it's greater than 5 given that X is greater than 3. Well, similar to what we talked about before, that is the probability of this and that. The probability X is greater than 5 and greater than 3, just like the last chapter, greater than 5 and X is greater than 3, over the probability of the second one, just like that formula from chapter 5. But what's another way of saying greater than 5 and greater than 3? If I told you something was greater than 5 and it's also greater than 3, the easier way of just saying that, well, it has to be greater than 5, over the probability that X is greater than 3. And so you'd say, okay, well, the probability of greater than 5, we just found that to be 2/7. All right, what's the probability if you were to randomly select a point in this rectangle to be greater than 3? Well, greater than 3, the area greater than 3, that'd be 1, 2, 3, 4. That would be 4 out of a total of 7. So and then when you simplify that, that would just be 2/4, and so it's 0.5 or half. And that sort of makes sense, I would think. If you're randomly selecting a number between 3 and 7, what's the probability to be bigger than 5? Well, half of it's bigger than 5. So it would be that. So that is a uniform distribution. And then we've got the normal curve. And so a good thing about this chapter is it's going to thoroughly review us for all of the normal curve stuff, and it's using normal CDF, inverse norm, but in general, showing your work in with the normal curve problems is you have to draw the curve to show the shading and to find the relevant z-score. But there'll be a couple little new twists in this chapter. But so this says a standardized test is given to 7,814 fifth graders in Detroit, Michigan. The scores follow an approximately normal distribution with a mean of 8.3, standard deviation of 2.1. If you randomly select one of the students, find the probability of that. So you would immediately notice approximately normal. So what we've got here, just shorthand notation, we got an approximately normal distribution, mean of 8.3, standard deviation of 2.1. So that's what that notation means. And so we had this problem later in the year. So we'll draw our situation here. So this represents basically all of these fifth graders. And so we label it as normal. Always label your curve. And then in the middle is 8.3. And then, our sigma is equal to 2.1, so that goes with that. So that means right here, one standard deviation above the mean is halfway down this hill at that inflection point, and so that would be 10.4. And then at this inflection point here, we subtract 2.1, and so that's going to be 6.2. So right like that. So I've labeled it right there. And so what's the probability less than 5? So 5 is somewhere down here. So So I labeled this as 5. So the shading is there, right there. And so what you can do is we'll find the z-score for 5. And so the z-score for 5, so that's going to be 5 minus 8.3 over 2.1. Remember, a z-score is just your x value minus your mean over your standard deviation. And so that is equal to negative 1.5714. And so then you could go to table A. Of course, I'm going to use normal CDF with my calculator, but just using the table. So we would find that z-score and see what the area that goes along with it. So negative 1.57, we're just estimating this. And so you notice the graph at the top. This table is telling us the area that's to the left of our z-score, which is actually what we want here. So we'll go negative 1.5 and then go over to the 0.07 column. So we connect these two things, and so that's equal to 0.5082, and that's my answer. So we would say on table A, we get, and so what did I say? 0.582. No, I didn't. Oh, that's not right. It is 0.0, so it's 0.0. So it happens a little more than 5% of the time. In other words, it would be on the edge of what we would consider to be statistically significant, as we're going to talk about later in the year. Now, and of course, to use your calculator, or you could just do this. We'll use normal CDF, and so my left bound on this is negative infinity to 5. My mean is 8.3, and my standard deviation is 2.1. So that would be my lower bound, that would be my upper bound, my mean, and my standard deviation. I've labeled as normal. I've labeled my parameters. Don't just write the numbers. To get full credit, you have to label your parameters. And so let's do that with your calculator. And so you remember, so we go to the distribution menu, which is right above the VARS button. So we go second, distribution, normal CDF. We'll never use normal PDF. Normal CDF and inverse norm are the things we're going to use, but normal CDF. And so it is going from negative infinity. So I just hit negative and hit the negative button, not the minus sign, hit the negative button. So negative 1 EE99, or you could just hit negative 10,000, that would be fine. And so, my upper bound is 5. My mean is 8.3, and then my standard deviation is 2.1. And so thus we get 0.05804. So there you go. Basically, pretty much the same thing. I mean, these things, are sort of kind of based on estimates anyway. So there you go. So showing the normal curve and showing the shading is important in regards to showing your work and showing the relevant z-score. But from here on out, I'm going to use normal CDF in general on the AP Stats exam. If you properly state normal CDF and you properly label your parameters with mu and sigma, lower bound, upper bound, if you forget the Greek symbols, just write the word mean and standard deviation, and you get the proper answer, you would get essentially correct. So now this is the same thing as earlier in the year. What's the probability if I randomly select any point in this curve? What's the probability I get between 6 and 10? So that would be normal CDF. Between 6 and 10. So I go 6 to 10. That's my lower bound. That's my upper bound. My mean is 8.3. My standard deviation is 2.1, mu and sigma. And so for that, so we would say, so second distribution, normal CDF, and we are going from 6 to 10. So we would say 6 to 10. That mean that's standard deviation, and so we get 0.6542. So that would be 0.6542 right there. All right, and so now this is a little bit new. All right, I've actually tried to do some bonus problems like this. In a normal curve, the probability of one thing given another, and it's similar to what we did up there with the uniform curve. So what's the probability that we would get greater than 11 given that our x value is greater than 9? Well, that is the probability of both of those things over the probability of the second one. But what's the easier way of saying that x is greater than 11 and it's also greater than 9? It's just the probability that x is greater than 11. okay, divided by the probability that x is greater than 9. So in this chapter, that's the way we're going to handle these conditionals, probability one thing given another. It's just it's the probability of that over the probability of that. And so what is that? The probability that x is greater than 11. That's normal CDF. Greater than 11, so that would be 11 to infinity. Our mean of 8.3, our standard deviation of 2.1. I will show my work by going lower bound, upper bound, mean, standard deviation, like that. And so when I do that, I get 0.09927 approximately, okay, divided by normal CDF, and then greater than 9. So it'd be from 9 to infinity. Mean of 8.3, standard deviation of 2.1. Label those lower bound, upper bound, mean, standard deviation. And so that ends up being about 0.36944. When you divide those things out, you get about 0.2687. And so there we go. So essentially what that is saying on this curve, if you randomly pick a point above 9, you randomly pick one of these points bigger than 9, what's the probability that it's going to be bigger than 11? That's what that is answering. And then this is an inverse norm problem. What value is smaller than 30% of values? So when you think about the curve here, so it's smaller than 30% of values. So that would be, we're given the area. See here, up here, we're finding the area. So that's normal CDF. Inverse norm is when you're given the area. And so you'd say, I want this right here where 30% is bigger than that. And so that is, in essence, the 70th percentile. Because if 30% is bigger, that means 70% is smaller. So it's the 70th percentile. And that's what inverse norm does. In essence, tells us percentiles. And so we will do inverse norm. And then I'll just use the left area, 0.7, label that as left area. And then your mean and standard deviation, 8.3, label that as mu, label that as sigma, and let's see what we get. So let me enter those values. And so I would say, okay, so I go distribution, inverse norm, the next one down, inverse norm. So like that, the area is 0.7, and then it is 8.3 for mean, and standard deviation is 2.1. And like I said, I tend to use the left area, and some calculators don't give you this option of going left, center, or right, but I'll use left area. But anyway, and so in this case, I get to 9.401. So this would be 9.401. And what are our units? So these are test scores here, so there's really not a unit. But you always look at it and see if it makes sense. You know, someone that is only being outscored by 30% of people, well, they're going to be above average. All right, they're in the 70th percentile, and sure enough, they are above average. So that seems to make sense, that score. All right, we did this earlier in the year. All right, what is the IQR? The IQR is equal to Q3 minus Q1. All right, in other words, the 75th percentile minus the 25th percentile. The Q3 is the upper quartile, all right? And of course, quartiles quarter the data. And so Q3 is the third one, the 75th percentile, and Q1 is the 25th percentile, the lower quartile or the first quartile. And so the way you find that is inverse norm. So you do inverse norm of 0.75, and so mean of 8.3, standard deviation of 2.1, label those. So that is my left area. That is my percentile, my left area, my mu and my sigma, minus inverse norm. So inverse norm of 0.25, mean of 8.3, standard deviation of 2.1. So that is my left area. Label that as left area. Label that as mu. Label that as, so I do the same thing here. So if I do inverse norm, 0.75 now, 0.75, left area, that mean, that standard deviation, and so I get 9.716. So this is running out of room, 9.716 minus, and if I do second entry, like if I hit second entry, enters the last command entries right above the enter button, and then I can just scroll over and change this to 0.25, and so it's 6.884 approximately, 6.884, and so that would be, when you subtract those two things, the IQR would be 2.833. So that is the That is the IQR. The other thing you could do very quickly, by the way, is to use, realizing it's the 25th percentile, the 75th percentile minus the 25th percentile. So you could go second distribution, inverse norm, and just do the middle 50%, go 0.5, and do the center 50%. So it's going to give you an interval that contains the middle 50% of the values, which is going to be the 25th percentile to the 75th percentile. So if you could enter like that, and it'll give you those two numbers, and you can just subtract them and get the IQR. But some calculators don't have that option. So now let's get outliers, and I did not leave myself enough room, really. So anyway, I wanted to get this on one piece of paper. So remember outliers, and so this is a very important concept in stats. Outliers are this. They are any value that is greater than Q3 plus 1.5 times the IQR. So this is really good to review from Chapter 1. Or anything that is less than Q1 minus 1.5 times the IQR. So in this particular situation, so outliers on the high side, so this would be 9.716 plus 1.5 times 2.833. And so anything bigger than that, that would be anything bigger than 13.96 would be an outlier. Or if we did this on the lower end, it's going to be Q1, which is 6.884 minus 1.5 times 2.833. And so that is going to be anything less than 2.634. So anything greater than that, anything less than that, or outliers, as we would call them, or unusual, really greatly unusual values that are outside the pattern, really, of the other numbers that would just really unlikely to happen. And then lastly this, and this is, we didn't do one like this earlier in the year, it says how many of the fifth graders. Now realizing, and in this case, we've got 7,814 fifth graders. So how many did scored greater than 10? All right, now what we've been finding earlier in the year is the percent or the proportion that are bigger than 10, and we can find that. And so we'll find that, the normal CDF from 10 to infinity, our mean is 8.3, standard deviation of 2.1, and yes, we're going to label it every darn time. Lower bound, upper bound, mean, standard deviation. And when we do that, we get 0.209107. And so about 21% of them did. So to find the number that did, we'll multiply that. And so we would say 7814 times 0.209107. And when we do that, we get that it is 1,633.96. And so what we will say is 1634. We'll say that many students. That's it. That is section 6.1. I wish you much success in regards to this section, in regards to random variables. Thank you for watching this video, and have a nice day.